All right. Okay. So these days everybody talks about artificial intelligence. Everybody talks about big data, and so the focus of my talk, what I'll try to do for the next 45 minutes, is to sort of do a scavenging task of trying to give a overview of the history of data analytics and data science and some of the beautiful techniques that have impacted data science from small data to big data. I will also give a very brief introduction of what big data is. However, this talk is not about how we process big data, how we clean big data, but this talk is from a skeptic's point of view. Being a practitioner in the field for the last 10 years, I do have my views, some really strong ones, and I do have my reservations about the whole thing. So a lot of people see big data as a revolution, as a technological revolution, as a revolution in decision-making, inferencing, and things like that. While some of these are true, there are some flags that we need to be aware of. Okay, and that's where I am going to focus my talk on, by drawing examples from inferences in small data. Okay, all right. So the title of the talk is Small Data to Big Data, and these slides will be shared by Professor Nagaraj later on, and so you can have access to most of the open source material that I have been creating as I go along in this area. Okay, and these are free to use, free to read, whatever. Okay, so so you could see there is a subheading, and which says machine learning nuances. Is it an art or is it a science? That's a raging debate for some time, ever since those big brothers in deep learning came into limelight, and the group of Hinton, Bengio, and Goodfellow. And you know that Hinton and Bengio are Turing Award winners for 2019 for their contributions in deep learning. So I'll also briefly reference those as well during my talk. Okay, so as I said, this is just a fragmented timeline that I wish to present. And we start from pattern recognition in small data. That's what it used to be called in the 1960s and 1970s. There is no terms such as machine learning or big data or whatever. It just used to be called pattern recognition. Which is given a set of data which has different types of information. Okay, how do you discover the hidden patterns? And typically, if you look at a classic text of Duda and Hart, right, in the 1973 classic test, and some of the other textbooks around that time, you will see most of the examples that are given in data science and data inferencing are examples which do not even last a page. So which means there are like a finite number of rows, like only 10 or 12 rows. So that's as many data points as you could get. And there are a few columns. Okay, all right. However, if I do not have enough data corpus, it's a challenging job to draw inferences from the data as well, okay? And both in terms of accuracy, also as in terms of scalability, okay? So now the problem is when the big data pattern recognition emerged in late 1990s, early 2000, and now because of the predatory mobile apps and all kinds of large internet service providers and big companies like Google, Amazon, and Microsoft are in, you do have your data, a lot of data, whether you realize or not, which is being accessed and being processed in the backend. Whether you are aware of this, whether you are not aware of this, it doesn't matter, okay? So the landscape has changed massively. From a few rows, it is now a million rows, okay? So my question is, and typically there should be a question that has the methods changed? Have you really need to do a complete overhaul of the methods that were so elegant, okay? And while porting some of these inference techniques from small data pattern recognition to big data pattern recognition, what exactly did we miss? Okay, what are the things that we have been able to port and what are the things that we haven't been able to port? Okay, and there is a strong underpinning in my talk that I strongly believe, and this is science, that the elegance in the methods, you cannot ignore them. okay? And somewhere during the talk, there would also be a mild critic. I mean, I think it's a mild critic. Some people might find it's a very strong critic of deep learning in big data era, right? And the silver line, however, I will present a silver line at the end, which is the beauty has started to re-emerge because people have been too preoccupied with the architecture and the data pipelines and the ways to collect and cluster and clean the data, right? And also a lot of people started believing in whatever works paradigm, right? However, there have been a few setbacks in the big data inferencing in the last 3-4 years. And one of them is a very recent setback. I will talk about that as well, which is forcing people to rethink their strategy, okay? So which means, I mean, some of the beautiful things that were existing in the small data pattern recognition and which we chose to ignore in big data inferencing are actually coming back, okay? All right, so this is roughly the highlights of my talk. And this is a sort of a bird's overview. I mean, some of the data science applications, and it doesn't really, some of these data science applications are not restricted to big data alone. They actually started from, small data. And, I really don't intend to go through all of this, but some very popular application areas are, medical sciences and health sciences and business, customer businesses, e-commerce, right? I mean, and there is this self-driving cars. And then there are, since we talk about e-commerce, there are lots of issues in e-commerce. One is, I mean, how efficiently you can access data of customers and group them into certain clusters or groups so that it is easier for you to sell your product. I mean, it's basically targeted advertising kind of a thing. And one of the strongholds of that e-commerce retail business chain is customer segmentation, okay? And while this is a new term, this customer segmentation is something which was thought of and addressed in 1950, actually, okay? Late 1940, early 1950, by an Indian data scientist. I'll come to him, okay? And then there are lots of, since you tend to do a lot of online transactions, there are fraudsters, there are hackers which try to steal your data. Okay, so a lot of anomalous behavior needs to be detected, all right? Okay, so generally these are all data science applications which form the core of either small data pattern recognition or big data pattern recognition, okay? All right, the difference is in the scale. So, well, I mean, since we started talking about customer segmentation, so let's sort of, see what it is. So what do we know of customer segmentation? So let's say I run an online store like Amazon, right? And I do have a bunch of information about a lot of customers that visit my site and buy things from my site, right? And based on some demographic and cultural information, based on some other information such as age, educational qualification, etc., I intend to group customers into different groups or clusters, okay? All right. Now, when you try to group people together, your primary intention is what? Your primary intention is to find out the distance between two customers, right? I mean, physical distance, right? Okay. Distance in the sense, it doesn't have to be a physical distance. It could be sort of in terms of their, likelihood of similar interest and things like that. Okay. And then there would be some customers which would be really far away from another set of customers. So they should be clustered in a different group, right? So measuring distances will help us in this customer segmentation problem or a clustering problem, right? Now we know there is this really old and classic Euclidean distance formula, right? Which helps us find distances between 2 points. Later it was shown that, well, if you can find distances between 2 points in 2 dimensions, I mean, you could actually extend it to 3 dimensions, and then you could also extend it to n dimensions. I mean, n could be anything, right? So, I mean, is this a good way to find out whether two customers are alike in the sense that they are really, I mean, spaced not too far apart from each other, and then there are 2 other customers who are really spaced far apart? Okay. Now, the problem with such inferencing is there's a very simple and brilliant concept that was proposed much later by Prashanta Chandra Mahalanobis with his Mahalanobis distance. So people have been using Euclidean distance, and let me tell you, this is the most popular distance formula that people use in big data and small data analytics, okay, even today, right? Okay. However, there are a couple of problems while using this sort of distances. One is, like, for example, let's say you have a two-dimensional system where along the horizontal axis, you keep the customer age, right? Okay. And on the vertical axis, you keep the customer educational qualification. Okay. All right. Now, also you can add another dimension or another axis where you keep the customer average annual income or monthly income. Okay. Now there is this question of correlation in dimensions. Are these attributes based on which you want to cluster customers, right? Okay, for your product, are these attributes correlated? And if these attributes are correlated, will that impact my decision-making process? What is my decision-making process? My decision-making process is there a targeted group of customers whom I should be able to sell a popular jeans product or a popular soft drink product, okay? All right. So there is this problem of correlation dimension because Euclidean distance is actually does not measure a distance between one point and a distribution, which is a set of other points. It just measures distance between 2 points. Okay, all right. So if, for example, naturally speaking, if the age of customers is more, then there is a strong likelihood that the academic qualification or educational qualification of that customer will also be higher. Like, for example, a customer of age 15, you don't expect that person to get an undergraduate degree or a master's degree, right? Okay. And also, if academic qualification of customers is like higher, there is a strong likelihood that the annual or monthly income of those customers will also be higher. So these are strongly correlated dimensions or attributes. So what is the problem in computing the distance between these set of points as it is without caring for the correlation dimension? What will happen is, naturally, if you have, and there is also a problem of scale that I'll come to in a bit. Naturally, what will happen is if you ignore these correlation dimensions, then what will happen is there would be undesirable people grouped into same cluster. Okay, all right. And so people who should really be grouped into same cluster will actually not be grouped into same clusters, right? And people who are not supposed to be in the same cluster will be grouped into the same cluster. Okay, all right. So this was a problem that people did not realize until they started talking about, really large data sets. Because if you have a small data set which has only 10 rows, you can sort of tag a wrong inference as an anomaly, okay? And you really do not look into the methodological flaw. But then Mahalanobis in 1950, he sort of figured this out. Even though, that's why I said the elegance. The guy had the vision to figure out, irrespective of the scale of the data, this is going to be a problem. If you scale this data up, and there was no high performance computing this time, there was no streaming applications, right? There is no Amazon, Netflix, there is nothing, right? Okay. So, but he had the vision to realize that this could be a problem if you have a large sets of data, right? Okay. And by the way, Mahalanobis did not even think about customer segmentation. Okay, he was purely thinking from a problem from the perspective of statistical biases. All right. So he proposed this. Now let me sort of. I know that this is a diverse audience. So let me sort of say the. What are the problems of using an Euclidean distance? Because Euclidean distance does not care whether one particular dimension or one particular attribute is more important compared to another attribute. So it just treats everything with equal percentage or equal weightage, right? Okay. So now suppose you have a data set where area of an apartment, you have a bunch of data set where area of apartment in square feet and their corresponding prices are given. Okay. Now you change that, and instead of representing the area in terms of square feet, you are now representing the area of the apartment in terms of acres. So what will happen? When you represent data in terms of square feet, you'll have like 700 square feet, 900 square feet, 1,000, 1,400 square feet, and there is a price, right? Okay. So this, imagine this couple as a pair of data points in a two-dimensional plane. Okay. Now you have some other property listings where the listings are made in terms of acres. I mean, the land area in terms of acres and the price. Typically, if you represent land area in terms of acres, right, you'd have sort of like 0.003 acres. You understand the problem in the scale differencing, right? So if you do not take into account the scale differencing, and if you simply compute the Euclidean distances, what will happen? Obviously, I mean, this will lead to a wrong inferencing, right? The reason why this happens is because you haven't made the scale of your data accountable. So you haven't rescaled your data. So Euclidean distance, naturally speaking, are not naturally endowed to handle this kind of scale anomalies. So it will compute distances as it is. So here comes Mahalanobis. And I mean, if you just, I mean, basically he also computed Euclidean distance, but he did a number of things before he computed the Euclidean distance, right? I mean, if you look at the formula, I mean, don't be bothered about the math behind it. But I mean, my intention is, if the dimensions which are columns in your data set are correlated to one another, which is typically the case in real world data sets, the Euclidean distance between a point and the center of the points, which is a distribution, can give little or misleading information about how close a point really is to a cluster. So this point is actually typically a customer, right? And what you are trying to do, you are trying to figure out whether this customer belongs to cluster 1 or cluster 2 or cluster 3. But the way you are computing the distance between this customer and a set of other customers is completely wrong if you stick to Euclidean distances, right? So here comes Mahalanobis. So what does he do? So he basically, what he does is a multivariate equivalent of the Euclidean distance. Okay, so let's see how what he has presented is sort of solves the problem. Okay, so you see the first term on the right hand side, which is x minus m, right, is basically essentially the distance of the vector from the average of the data points. And then there is the C inverse. This C inverse can be interpreted in different way. The way I interpret this is basically it's a covariance matrix, which you can think of this as this x minus m, you are dividing this by the covariance matrix. Now the question is, why are you doing this? I mean, what is the effect of dividing the covariance? Okay, the effect is the following. The effect is if the variables in your data set, the attributes, which is customer age, academic qualification, annual income, blah, blah, blah. If the variables in your data set are strongly correlated, then the covariance will be high. So if you divide by that high number, what will happen is it will effectively reduce the distance. Likewise, if the variables are not correlated, then the covariance is not high and the distance is not reduced. So effectively, it addresses the problems of scale as well as the correlation of the variables. Okay, and using this, he essentially solved a very critical problem which people realized 40-50 years later when they started dabbling in big data. And this is not only limited to customer segmentation applications. This is used in multiple other applications such as anomaly detection, such as one class classification, which is interesting. Like one class classification is sort of, I mean, it's sort of this, that you have a really small data set which is annotated. And then you have a really large data set which is not. So what you are trying to do is that use the labels that you predict from that small data set and use that to label the large data set. Okay, right? I mean, I'll give you an example. Like a lot of anomaly cases in industrial systems like GE, I mean, Nitin was in GE, so he will know this. GE produces, boilerplates, right? I mean, those are really expensive stuff, right? So generally speaking, when the boilerplates are working, which they are supposed to work, they will work for 20 years, okay, and nobody cares. The moment it blows up, I mean, it starts, sending shivers in your spine, because then you are looking at a multi-million-dollar replacement, right? So this is one incident that happens in maybe like 20 years in a lifetime, right? So how do you segregate such a thing? So Mahalanobis distance also helps solving these kind of problems. Also, most importantly, forget any of the business data applications, whether in small data or big data. His resounding contribution to this data science is the removal of statistical bias, okay, when you compare different dimensions, okay? So to my mind, he is India's first and probably the finest data scientist, okay, who never really cared for big data, but his inferences and his methods have been immensely helpful, both in small data as well as big data inference, okay? The point being, he proposed a method that is simple and elegant, right? Okay. And unfortunately, you will not see wide applications of this particular method. You still see people use Euclidean distances left and right when they try to solve clustering problems, even on multidimensional data, right? So this is sort of ironical, but people know, like for example, Nitin works on EEG data. I mean, so there is this disease known as arrhythmia. So even in arrhythmia detection, people have used Mahalanobis distances, right? Okay. So there are applications, but then my point is, as I said, I mean, my talk today is about a little bit about skepticism of how things are being done in the big data landscape, right? So one of the problems that I see is that people do not really weigh in the importance of methods which are really scalable from small data to big data. Now, you may ask a question that, you have to invert a matrix. I mean, in really a big data scenario, the matrix inversion is a costly operation, but those problems can also be solved. There are eloquent and elegant solutions of how to compute large matrix inverses, right? Okay. So as long as we care about those methods. Okay. All right. So here is the big data landscape. It's basically typical big data landscape is a Google Analytics point of sale, right? I mean, you are analyzing a lot of different types of data together. You have LinkedIn posts, you have tweets, you have Facebook, you have data coming in from your mobile, you have data in audio, data in video, everything. So the nature of the data is multimodal. So that's what this V cube idea in big data comes into picture. This one of the V in this V3 stands for veracity, which is different types of data. And then the other V stands for volume, the scale and the size, okay? And the second one stands for velocity, which means the rate at which new data comes in. And this actually calls for some really fast learning algorithms. Now, what really happened in the last 20 years is that people thought, and they were right to some extent, that one of the ways to deal with all of these three together is to propose new pipelines and architectures. I don't disagree with that, okay? But I don't know whether that is enough. So what really happened was, in the search for new architectures and pipelines, people almost forgot that you are ignoring one of the core in the data inferencing, which is the method, and how efficiently those methods solve really, really challenging problems, okay? So my question is that, is new architecture is a solution? Yes. Is it the only solution? The answer is no, okay? Now, one example I want to give is, because I work in astronomy a lot. I mean, one of the things that have impacted astronomy, modern astronomy in the last, 15 years, okay, and I would rather say in the last 5 years, is the implosion of huge amounts of data, okay? And this is mostly due to NASA's missions, okay? Not only NASA, and I know I'm not supposed to say this because, I mean, it's probably at the cost of being labeled anti-national, but a lot of these new data that had come into our scientific fold is also because of Chinese space missions, okay? I mean, they have done an amazing job in gathering data, okay? And some of the things they have actively contributed to is one of the projects where NASA's mission failed in 2012 and the Chinese guys took over. So that mission is known as the Galaxy Evolution Explorer. Currently stands at 30 TB of data, 30 terabytes of data, followed by, and this is complemented by the Sloan Digital Skies survey, which is about 40 TB, and the Large Synoptic Survey Telescope, which generates 200 petabytes of data. Okay, and there are larger data. There are data in exabytes as well as so one of the questions that naturally comes in: how do we process such scale and volume of data? Okay, is there a data format? The answer is yes. The astronomers have also figured this out. There is an ASDF, which is known as astronomical data format, which basically, if you have so much data, remember this data is not only text data. The data could be images as well, because satellites capture a lot of images, right? And you cannot really process most of these images in your data pipeline. You have to do some flattening and stuff, right? So all of this is done in the back end, right? But the question is, and then what we do once we have the ready and clean data, we just forget everything that we have learned in the last 50 years and just start relying on the architectures and the pipelines. Okay, some of the consequences are disastrous, and I'm going to talk about those in a minute. Okay, so what's really the difference between big data scale and small data? Small data can also scale up, but the rate at which small data scales up is not as fast as the big data, right? Okay, so one of the difference between small data and big data is the volume and the veracity and the velocity. Okay, are there much differences between the methods? I don't know. I don't think so. But the most important question that I want to pose is, while you move from small data to big data, do you get rid of the elegance? No. So what do you need to do in order to handle the velocity and the volume? You need to learn fast. You need to learn online and not necessarily deep. Why do I use this particular word deep? Because deep learning is once again another buzzword that has been hitting the deck, quite severely for the last 10 years. And while some of the deep learning solutions have given amazing results, okay, there are other things that we need to consider about deep learning. Okay, so the evolution from small data to big data, one of the harbingers of this evolution, one of the agents of change in this evaluation in terms of handling and predicting inferences from big data is deep learning methods. Okay, all right. So which is what I'm going to talk about next. Okay, so it's really, really deep neural networks. Neural networks, as you know, is a sort of a mimicry, and I don't say a very elegant and realistic mimicry of the human brain, but it just uses the idea that there are human brains as neurons and neurons interact. So you sort of line up your neural network architecture as some sort of an input layer, and there is something that triggers, and there is an output layer, and between the input and the output layer there are some hidden layers. Okay, and you imagine this as a fully connected neural network, which means all the input units are connected to every unit in the hidden layer, and then if you have more than one hidden layer, all the units in that layer is also connected to every unit in the next layer, and so on and so forth. So the question is, how many hidden layers do we use in order to infer efficiently? The answer is we don't know. Okay, all right, the answer is we don't know. So people keep on experimenting. So people keep on experimenting with number of hidden layers, number of neurons, number of connected weights, and so on and so forth. Okay, all right. So there is this funny comment about this Dan Ashley. He's a professor at I think University of North Carolina, Chapel Hill. Okay, from a social science perspective. I mean, he works a lot on behavioral economics. He says big data is like teenage sex. Everybody talks about it. Nobody really knows how to do it. Everybody thinks everyone else is doing it, so everyone claims they are doing it. Okay, all right. And then this is followed by Professor Michael Jordan, whom I have a lot of respect for. He's a full professor and a chair, the Department of Statistics and Machine Learning, University of California, Berkeley. He says that society is about to experience an epidemic of false positives coming out of big data projects. Okay, so what he really means is, without doing really vigilant statistical inference and without caring about the error bars, right? I mean, where you are actually making errors, if you rely on deep neural networks, then it will lead to false, meaningless inferences. And he also says it's a certain fool's gold element to our current obsession. Okay, so here comes the skepticism. Okay, I mean, I do not want to run it down because I see there are other talks lined up which says, AI is a revolution and there is a harbinger of change. While I do not completely disagree with any of the claims, I think what we are missing is we haven't been able to foster a successful relationship between the methods and the architectures. Okay, all right. So first of all, I mean, there is this cost. There is this cost of setting up a really efficient pipeline for processing deep data. And this is a typical infrastructural specification that I know personally, because in BITS Pilani, we have set this up. We call this Kosambi cluster. I don't know if you have heard of Kosambi. Professor Damodar Kosambi was an eminent statistician, but he also, being a statistician, he had made immense contributions to political science, social science, and behavioral economics. Okay, I mean, he was a son of the soil in Goa, so that's why this cluster is named after him. Okay, so the budget is approximately 75 lakhs, and this is not really an extremely high-end, high-performance computing setup. Okay, this is something that we can use to get by. If it's really, really large data scale, then this is something that we cannot really completely rely on. We have to go and seek the services of Amazon Web Services or Google Cloud and so on and so forth, right? Okay. Okay. I mean, I have said enough bad things about, I mean, not bad, I have critiqued the big data architectures, but let's also, talk a little bit about how good they are. They're really good in the sense that, really dense networks for processing computer vision data sets. Actually, the emergence of big data and the emergence of deep learning techniques is mostly due to the computer vision data sets, and the comes from a fashion industry perspective and lots of other industries where people really want to process images, very, very large image data sets, and they want to predict, right? And this is not only from a business perspective, even in astronomy, we do that. I mean, there are millions and millions of images of galaxies and hot stars and quasars, and we would want to classify them, right? And there have been some really sophisticated architectures and models that have been proposed. Convolutional neural network being one, recurrent neural networks, attention models, LSTM for time series data, so on and so forth. Also, what the big data community has done along the way, as while they process this kind of data in the pipelines, they have also prepared a very extensive set of data sets for other people to experiment. So some of these data sets are MNIST, Cypher 10, Cypher 100. There is an MNIST fashion MNIST data set as well. And there are lots of other data sets as well. Okay. So the question is, we say that these neural networks are really expensive, right? Okay. And they consume a lot of time and resources, okay, while we train the network. So we tolerate this, we tolerate the cost, we tolerate the other stuff, because the accuracy a lot of times comes out to be really good, which the traditional small data pattern recognition techniques have trouble achieving it, right? Plus, there are lots of nonlinear problems which are difficult to analyze, and these deep learning architectures and these deep learning methods solve them quite well, okay? But that's not the end of the world. I mean, there are a lot of other things which they actually don't do quite well, okay? So this is the good stuff. Here comes the bad stuff, okay? Now, the way deep learning really works, basically this is really a function approximator network. So you are trying to infer a function, okay, from your large number of hidden layers and the connected components of neurons and so on, right? Okay, and you want to do it in such a way that what you're predicting and what your target is, the distance between those two are really, really small. Okay, so this is really an optimization problem. I'll come to that in a bit, right? But along with computer vision and image processing data set, there have also been a lot of text data, really natural language data, like a lot of tweet processing, LinkedIn post, and so on and so forth. There are interesting problems such as hate detection, there are interesting problems as in, can you detect terrorism activity from tweets and so on and so forth, right? And in order to do that efficiently, you have to really process a really large corpus of data. Okay, so typically the state-of-the-art natural language processing models have a very long training time. Okay, but what is the cost of this? So there is a recent MIT technology review by Karen Howe. Okay, and where they have shown, they basically reported something which says that a standard NLP model, okay, which required a certain number of aggregation models over a certain period of time. Now, when you are done with training over a 6-month period, the CO2 emission is approximately 78,000 pounds. Imagine. I mean, let that sink in. And the process actually is potentially can emit 626,000 pounds of carbon dioxide equivalent, which is approximately 5 times the lifetime emission of the average American car. So it's like training a neural network model, standard neural network model, to achieve what you want to achieve is equivalent to as if you are running 5 cars in your household. I mean, unless you are a really, really rich guy, I haven't really seen average American households having 5 cars, right? Okay, so imagine the cost. And even after doing all of that, I mean, there is a funny precedence. I have seen this tweet somewhere, is that there is this guy who was traveling from Bangalore to Calcutta. Okay, so he was traveling on an airline, and what the airline had done is that they sent his baggage to Hyderabad. I mean, he was traveling to Calcutta, but his baggage was sent to Hyderabad. So he writes a sarcastic tweet saying that, "Thank you, this airline, for my travel from Bangalore to Calcutta and sending my baggage to Hyderabad." This is sarcasm, right? Pure sarcasm. To which the airline's customer care replies, "Thank you very much. We appreciate your support, and we continue to, we hope that you will fly with us in future," and blah, blah, blah. And then the guy replies to that tweet in that really just one word. So this is a standard natural language processing model, which is like equivalent to 5 average American car emissions. And this is the inference that you are actually getting at the end of it. Okay. I mean, this is still okay. I mean, your models can go wrong. They can make wrong inferences. But the ugly part is that tiny image data set. I'm not sure if you're aware of this. This came out of an MIT CSAIL laboratory housed in the Department of Computer Science. This is a very, very well cited data set. I think it has like close to 100,000 citations. Okay, all right. They call it a tiny image data set. It has about, close to like more than 100 million images, okay, scraped from different sources, right? And arranged in different categories. Okay, all right. Now this, on July 1st, 2020, 2 researchers from University College of Dublin dropped a bombshell. What they show is that you are training, because the idea is you have a very large corpus of image data sets and then you feed in new images, right? Okay. The algorithm, the predictive algorithm, the big data predictive algorithm should be able to predict the level of that new image. So suppose you have images of flowers, houses, men, woman, child, parks, gardens, so on and so forth, right? Okay. So naturally, this image data set contains images of women, images of men, images of women carrying a child, right? Images of animals, right? Okay. What really happened is you add a new test image. Let's say there is an African American woman with a child in her lap. So the label that turned out is an N word. You understand the N word, right? Okay. So that was the predictive labeling of that deep learning architecture curated out of that tiny image. They call it tiny image data set, but it's really large. It's an extremely large data set of images, right? Well, it turned out that monkeys, while training, monkeys are also trained with the same label. So you are labeling black people with the N word, you're also labeling monkeys with the N word. Okay. This is not the ugliest part. The ugliest part is women holding their children, right? Okay. Women in bikinis holding their children. As if women, they wear bikinis, they cannot hold their children. It almost sounds like that, right? They are labeled as that W word. In the parts of the anatomy labeled with crude terms. What's the point? I'm not getting into the ethics of it. From an ethical point of view, it's a nightmare. MIT apologized. They immediately withdrawn the data set. So if you go and search in that CSAIL lab, you won't find the tiny image data set anymore. right? But I think that should not be the end of the world. I mean, MIT should be made to pay. I mean, they have made a huge mistake. The official statement of MIT was that they did not actually look at the training levels. I mean, come on. Okay, so anyway, the point of this slide is not to, focus on the ethical digressions, but to tell you that after all this brouhaha, your big data architecture, your big data inference models are as good as your data. You haven't really figured out a way to cross-check the training levels. Even, I mean, imagine this, when this data set has been used by at least 100,000 people, right? And it hadn't come to any one of them that whatever they're getting is wrong. And there is this is not really ugly, but I also find it really, really objectionable. The word2vec, which is also being used, and wordnet, which are sort of, word-based, natural language-based data sets, they invariably tag mothers as homemakers. It's almost like a CBSE textbook, right? Why are we outraged about a CBSE textbook which shows women as homemakers? I mean, your model is also doing the same thing, right? So after all of this, what has your big data machine learning models done? We are just processing. I'm part of this as well. I'm part of the community which makes this mistake. We are processing only the volume efficiently. We are not bothered about the quality of our inferences. Okay, so this is where I sort of wanted to focus. Okay, I don't know how much time. Okay, I still have 15. I think probably I have another 15 minutes, right, Nitin?
Snehanshu, maybe another 10 minutes.
Another 10 minutes. Okay.
Is that okay?
Okay. Right. Sure.
Yeah,
so anyway, I just so from this big data landscape, right? I mean, I just wanted to just point to another master who did not care about big data much. By the way, he is now processing big data. This is Professor Vladimir Vapnik. Okay, a beautiful mind. He's heading one of the major divisions in Facebook research. Okay, he's no longer at Bell AT&T Labs, right? Okay, and the timeline, he started working on a problem in 1964. He finished it up in 1992. It's a 28-year timeline. Okay, unfortunately, because of the volume of big data, we rarely can afford such timeline to come up with a beautiful solution. Okay, all right. So what he had done was he was trying to solve a problem, okay, where I will just straight away just go to the data. I'll come to these two gentlemen in a bit. So this is a sort of problem he was trying to solve, right? He was trying to solve two different classes of data. He was trying to figure out a geometric solution, nice geometric solution, without doing much geometry, that you should have one class of data separated by a large margin, and you should have another set of data separated by a small margin. And this large margin actually takes care of the region of confusion, so that there is no way these green guys come close to the blue guys. Okay. Well, this is good as long as your data is sort of separated by a line, which you can see. If the data is not separated by a line, if it's multidimensional data, there is a beautiful technique that he later devised, much later in 1995, right? And the reason why I wrote this is because he started solving this problem in 1964. When he started attacking at this problem, he was trying to solve an OCR problem, optical character recognition problem. Okay, all right, which means, I mean, you know what an OCR is. I mean, he's trying to figure out patterns from the OCR, right? And when he started looking at a problem which was sort of like this, okay, this is actually an example from astronomy. So basically, this is stars, quasars, and galaxies, and you can see the violet ones are the stars and the yellow ones are the quasars. So the way these images or these data points are distributed in space, I mean, there is no way you can separate these by a line, by drawing a line between the two or a margin, right? So this is an classic example where Vapnik's method would fail. Vapnik knew this. So what he did was, he went back to these two gentlemen. One of them is David Hilbert, the founding father of modern mathematics. And much before that is this Professor J. Mercer. Okay, he was a peon, by the way, in the post office. Okay, all right. So this guy sort of wrote a paper in 1903. I mean, That's a very, very abstract paper, right? But Vapnik found out there is some relation between what he was doing and what this guy has done 61 years before he started working this problem. And he immediately put it up. That's why I call this a master class of 1903, which was later used beautifully to solve nonlinear margins. Okay. So this is something. Now what happens? People tag this method as a method which is really computationally expensive because you have to you do a lot of dot products, inner products, and blah, blah, blah. Now, 25 years, almost 25 years after Vapnik has written this method, what happened? In the big data community, they realized that, oh, this method is actually useful in big data inferencing. So it has come back in the form of neural SVM, support vector machines in neural networks. Okay, all right. So you see what you have. So you have learned the hard way by making disastrous predictions, both from a technological as well as ethical perspectives. You realize it the hard way, right? That the classification problems are really optimization problems. Okay, all right. And the more elegant solutions you propose to solve these optimization problems, the better you are, both from a small data as well as a big data perspective. So there is this 100-year span. You may ignore the mathematics, forget the mathematics, okay? There is this 100-year span between Mercer, Hilbert, and Vapnik that connects the dot to solve incredibly hard problems in big data inferencing. Okay, all right? I mean, I don't have the time, but you can, just for the, I knew that I wouldn't have the time, but just for the sake of completeness, I have included this. And more importantly, just look at this. So in lower dimensions, so basically the whole idea was in lower dimensions, because big data is about large dimensions, right? I said in the preliminary slides of my talk that it's all about large dimensions, okay? And dimensions add to the veracity of your data. So in large dimensions, I think somebody's mic is on. So in large dimensions, so what is not possible in lower dimensions, so you can see this image, the first image, right? There are two types of data and there is no linear boundary, right? This is not possible to solve in lower dimensions. So what Vapnik did, by using that master class from Mercer, he projected these data points to a higher dimension. And you can do it to any dimension, any higher dimension as possible. And the moment he did that, you can look at the image below. The non-linear decision boundary has been converted to a linear decision boundary. Beautiful, right? It's a very, very simple and elegant concept that, and this is what people realized. The people in the big data, people like me, lesser models like me, realize that we can use this in inferencing the big data decision problems. Okay, so I think I'll finish with this. Is that what I think when we migrate from small data inference to big data inference, the central theme remains the same. We optimize, optimize, optimize. Okay, you have to come up with new methods in optimization, solidly backed theoretically, so that your prediction errors are low. Okay, get rid of expensive architectures. Okay, and do something which Professor Nitin Nagaraj has been doing for some time, which is single shot learning. Try to learn in single shot, right? That will reduce considerably your learning time and effort, carbon emission, backend infrastructure. You might lose some in prediction accuracy, but that's okay. There are domain experts who will come in and fill in the gap. Don't expect your machine to do everything. Okay, all right? And there are certain things, there are certain terms in deep learning, big data optimization, which I call as bandits. So there has to be a way to tame the bandits, which are the hyperparameters. Okay, and finally, I know most people don't like this part of my talk. All of my talks is when I say what you need to know in order to be a very good big data scientist or a machine learning scientist, is that you need to know all of this, starting from advanced calculus. And this is something most people don't like, which is fine. Okay, all right. So when we go to big data artificial intelligence, what are the performance benchmarks we should be looking at? Not only the accuracy, not only the loss, these are obvious things. We should also be looking at the number of iterations or epochs to converge to an optima. When you converge to an optima, your prediction accuracy is the maximum. Okay, your misclassification almost becomes zero. The other benchmarks that you should be looking at when you ran your algorithm and the methods, what is your memory and CPU utilization? Are you really utilizing almost 100% of all the resources that were given to you? Because if you are doing that, that's, I don't think, the right way to do. And also figure out how much carbon footprint is being caused by the method that you have just, developed, okay? What you should avoid: inferences that make no sense. Avoid certain ridiculous mistakes, like I gave that example of a tiny image data set, right? I will give also another example and then I'll finish my talk, which is I'll just go back to this particular image. Now, I said, right, the stars and the quasars, some of the stars and the quasars are really difficult to separate. So if you really don't care about methods and you don't really want to think hard about how to separate this, right, you can do a very simple solution. And that simple solution is there is one dimension which is known as redshift. Okay, if you use redshift as a feature or as a dimension in your training data set, this problem is really easy to solve. Okay, and in fact, you will get 100% accuracy. Okay, all right. So what's wrong? What's wrong with that? What is wrong with that is that if you really use redshift as a dimension to separate your stars and quasars, you actually don't need a machine learning engineer or scientist. You hire an 8th grader and ask him or her to look at the values of this redshift, and he or she will be able to tell you which one is a star and which one is a quasar. So that is wrong. So, and believe me, there are actually papers published in really top journals using redshift as a training feature. And they claim 100% accuracy, which is right. There is nothing wrong with that claim. But how you achieve that 100% accuracy is a big question mark. Okay, all right. So this is, it's a ridiculous mistake. And then there is also this aspect which I don't have the expertise to talk about. I am outraged by it, which is the ethical, social, racial misdemeanor that some of the big data AI algorithms are actually throwing at us. Okay, and MIT tiny image dataset is one example. There are plenty of other examples as well. Okay, so with this, I would like to stop. Just for completeness, there are lots of other slides which I included, and there are some really classic things at the end of the slide, because eventually these slides will be shared with you. Some of the classic papers that you should all read, or at least try to read, and some of the classic texts in machine learning and deep learning and big data analytics that you should read. And the last one, this is the only big data book that I like. It's written by Ullman, basically a compiler guy. And his second chapter, where he really starts talking about big data analytics, the method he starts with? Support vector machine. The method written by Wapnick. This is a big data textbook. Okay, all right. Thank you so much. And I'll now take your questions.
Yeah, Snehanshu, yeah. So thank you for a fascinating and thought-provoking lecture. I learned a lot of things by your lecture today. Just a couple of comments I thought I'll make. One is I really like this notion of elegance you made,
Right.
It reminded me of Hardy, Hardy's comment, right?
Yes,
that there's no place for ugly mathematics.
Exactly.
There's no permanent place, I thought. And the second thing was Kosambi, right? I don't know whether you know this. He actually was the first inventor of the single value decomposition algorithm. Not many people know this, but the single value decomposition goes all the way back to Kosambi, actually.
Actually, I think, Nitin, I know, because actually what happened was, that Mahalanobis distance, right? It is also used in PCA, right? Right. And then PCA, you can actually write PCA as a special case of singular value decomposition.
Right, exactly.
If you think about it, right? Yes. So when Mahalanobis was working on it, on using this Mahalanobis distance in PCA, I think Kosambi also at the same time, he figured out something similar. He did not call it singular value decomposition.
Correct.
But I know that.
Absolutely, yeah. Okay, we'll take up questions and discussion now. I think, thank you, really very fascinating lecture, very thought-provoking. So over to Aditi now, yeah.
Thank you, Snehanshu sir, for that enlightening talk on the methods of data science. And thank you, Nitin sir, for your comments. So now we are open for questions and discussion. I can see a number of questions here in the chat box. So I will go through them one by one, and then we can have a discussion. If the speakers want to add something to the questions that they have written, they can speak up once I read out their questions.
Aditi, I can also read the question. So, if it's okay, I can see the question. Yeah.
Okay. Yeah, sure. So first one from Ranjini,
Right. How useful or risky is the use of health data, according to you in healthcare delivery? Well, I mean, I think at least, you know, in healthcare, thankfully, there are certain norms that are in practice. Like, for example, when hospitals share data with you, because a lot of hospitals, like we work with Manipal Hospital, and Nitin also works with, I mean, Nitin is the best person to ask this question because he works with St. John's people, he works with NIMHANS and other guys, right? So when data is shared with you, it is really up to the health professionals to share the data, you know, in a responsible manner, okay? However, if the data is not shared with you in a responsible manner, I mean, I think even as a techno guy, it is your job to look at what sort of data is given to you. And if you think something is questionable, because there are some things which you absolutely do not require for your prediction, right? For example, a person's religion, right? If that data is present, I mean, in terms of like if that person has diabetes or not, his religion has nothing to do with it, right? And if that particular data is present in that data set, you should really go back and tell your provider that, you know, either you remove this column or I remove this column. At least in the USA, there is HIPAA, right? I mean, so there is a very, very strong regulation, you know, forbidding people to access personal data of patients. But in India, in a lot of the developing countries, this privacy issue is ignored. I mean, and the privacy issue very skillfully is tied to security only. Okay, privacy goes beyond security, much, much beyond security. I mean, there is a strong ethical component in privacy that we tend to ignore. So, I mean, I do not work a lot on health records, but whatever health records I worked on, like for example, low birth weight prediction, this is one health record that we worked on from villages in Andhra Pradesh. We made sure that, you know, there are certain things that we don't want in our data set. So it's definitely risky if you're not careful. Okay, all right. And you just in order to avoid an MIT-like situation, you really, I mean, you know. So there is this next question is, I don't know if I asked the question, Ranjini, but I mean, if you have some other question, you can, you know, email me. There is this next question from Abhinay. He says, can we use concept of fractals in really big data? Yes, you can. Certainly, right? Okay. In fact, if you're trying to, there is this reconstruction of landscapes. There's a problem in computer vision. Okay. So, and so basically, this is reconstruction of landscape is one. Reconstruction of artifacts. I mean, reconstruction of artifacts in heritage buildings is another problem. I mean, I can give you this example from Hampi. I mean, where there is a huge project funded by Department of Information Technology. I mean, cohorted by IIT, IISc, and ISI, if I remember correctly. And what they're trying to do was, you know, take pictures of different, you know, images on the buildings, okay, convert them to, and then do the processing on the soft copy, figure out what's wrong in each one of the images, and then use corrections on those images. And when your images are corrected, go back to the painters and architects and structural engineers, and they will just follow the corrected image, soft copy, of course, and you know, try to restore all those you know, monuments, right? So one of these process in this correction is use of fractals. So certainly yes. What do you think about ethical algorithms? How easy or difficult it is to operationalize ethics at the algorithmic level? At the algorithmic level, well, I mean, at the algorithmic level, you could write sort of a screening algorithm, which really will fan out the dimensions or the attributes that you do not need your algorithm. That is certainly possible, but most people don't do that. Okay, they think that the clean data. Now, when you talk about clean data, this clean data is purely from a techno point of view, right? The clean data does not mean ethically clean data, right? So if you really want ethically clean data, you should actually have to look at each one of the dimensions, okay, all right? And some of the image and vision data sets also have metadata. So you have to be really, really careful. This is what MIT is saying. MIT is saying that we did not have the time to look at the metadata. And I think that's rubbish. They knew all along, okay, all right, and they didn't really care, okay. So I don't think it is extremely difficult to operationalize ethics at the algorithmic level or at any other levels. It's just that we don't care, okay. So thanks for a thought-provoking presentation. Thank you. Since neural networks are trained on real-life data, which is inherently biased due to yes. How do we ensure this does not happen? Secondly, okay, how can we tweak data to make it bias-free and yet reflect accurately the state of the society? Well, first of all, as I said, if you get rid of unnecessary attributes, some of the biases are automatically removed.
Got you.
Okay, all right. And the secondly, how can we tweak data? I mean, by tweaking data, see, you cannot fiddle with data. The only way of tweaking data is to remove unnecessary attributes from the data. Okay. The other way is the tweaking the levels. I mean, you can do something at the leveling part, right? Okay. So that is possible. Okay. But it is extremely difficult to get rid completely of bias, because the society is misogynistic, whether we like it or not. Okay, and some of that actually sieves in, pours into the data that we actually create.
Right.
So there has to be.
Should I share that with you now?
Excuse me.
And anything apart from emails, if there is.
Hello, excuse me, who's that? Whose microphone is on? Yeah, please be careful.
Okay, then there is this question of, thank you for the excellent lecture. Thank you very much. I'm glad you liked it. The vulnerability of data in public space.
Works for me.
Right, training. Somebody is speaking, someone else is.
Yeah.
Have a nice day, both of you.
Excuse me, who's that?
Aditi and Nitin, I think both of you have the control. Both of you are co-hosts. You can mute someone, or you can announce, or you can remove that person, put the person in a waiting room. Okay, thank you.
The noise was, I think, by Chavi Sharma. If you can see it, I've muted
Anyway,
it.
fine. Yeah.
Don't. Thank you, Niharika.
Okay. Yeah, that's okay. So, I mean, I think Nazneen, right? Nazneen. The vulnerability of data in public spaces is frightening. How could it be addressed? Vigilance and the vigilance of officials at the right places. I mean, I think I said this enough number of times. I mean, it is the problem. See, if you look at data, now that you are using data from all public spheres, from public health from society, from different aspects of society. So I think one thing that is missing in this whole big data AI landscape is that we do not talk to experts when we take data from their domain. In other words, talk to a social scientist when you are using data from their domain. Talk to a public health professional. Talk to a humanities person. Talk to an ethics professor, right? We don't do that. Okay, and then there needs to be some protocols that need to be set up as far as this big data architecture is concerned. But this is primarily driven by big corporate interests, and their ethical considerations are worse than ours. I mean, yours and mine. They don't care. So this is mostly, I mean, in fact, there was a recent survey where it shows that most of the big data landscape, the ownership of the physical as well as the virtual infrastructure, is owned by 3 companies, Amazon, Microsoft, and Google, to an extent of 79% of all cloud infrastructure that exists in this world. Okay, I mean, do you think Amazon cares? I mean, whether if some woman is labeled as Negro? They don't. I mean, as long as it doesn't hurt their business interests, they don't care. So the vigilance has to come from the public sphere, from the public officials. Corporates will never care. Okay, all right. So I think there are other questions. It's a sort of a long question. With the development and progress in the manufacturing of artificial data storage, don't you feel that the human memory data storing capacities of brain have gone down? I don't have enough evidence to either agree or disagree with you. I'm not sure if there is a reduced capacity, a depleted capacity of the human brain. I'm not sure whether it's because of the artificial data storage. I think it's because of multitasking. I mean, I don't know that. I mean, you should ask this question to the people in the consciousness studies program. I mean, you should ask Nitin or Sangeeta these questions. I'm not really qualified to answer this. Do you find any impact of artificial data storage development on human brain memory? As I said, I don't know. I don't think so. But I actually don't have statistical or empirical or any other evidence to either support or deny your claim. Then the next question is Mr. Debaprasad Das. He says, can transfer learning? Which case? I'm not sure.
Sorry
Mr.
to interrupt
Das.
you, Snehanshu. I thought somebody has switched on the mic. Please, I request them to mute it so that he can take maximum number of questions. That's the idea, you know.
Right.
Thank you.
So Mr. Dash, I don't know which case you are referring to. Can transfer learning be useful in this case? If you are referring to inferencing from small data to big data, yes, I'm assuming that's what you are trying to refer to, right? Okay.
We can ask him, Mr. Das. Are you online? You could pose your question to Professor Snehanshu. Mr. Das.
Hello, sir.
Yeah. Please go ahead. Yeah, you can identify yourself.
Yeah. So my question is that can we use both the machine learning and AI concept like LSTM and SVM together in many applications, like LSTM or RNN for feature extractions and SVM for classification?
Yes. That's what people have been doing, right? I said that the SVM has come back. In fact, decision trees have come back in neural networks. You know, the funny part is, okay, all right. Yes, certainly. I mean, and one of the reasons why these things are coming back is that people have realized that, you know, they are, in answer to a question, I mean, you would see a lot of standard implementations of big data architectures where people set a number of epochs. They say 300 epochs. By the way, one epoch is one complete forward pass in your neural network and back, right? So people set standard 300 epochs. You ask them this question, why 300 epochs? They say, no, this is the standard one.
Yes.
Right. I mean, so I think what you should be asking is that if this performs well in 300 epochs, does it perform as well as in 30 epochs? If the answer is no, then there should be investigation as to why this is not performing as well in 30 epochs.
Yes, sir.
Right. Okay. Then the next question is Chavi Sharma. Is latent directional allocation and optimization technique? Yes. I mean, to some extent, yes. Yeah. Okay. Thank you for your insightful presentation. My question is how to take care of ethics in building a model. I think I have answered this question. Right? So if let me cite a recent case, a language learning app asked to translate a sentence which is, I am the least beautiful, to reach least mode. First, if anyone sees it as a problem, what could have been done in model not generate this kind of sentence? See, this is the thing. I mean, because if you, as I gave that airline retweet example, right? I mean, the volume and the velocity, these two things are the problem. So there are people which, I mean, so there is one way of, you know, approaching this from a syntactic point of view, and there is another way to approach this from a semantic point of view. I mean, both syntactic and semantic are actually not enough. So this is still a very premature, I mean, even in the context of natural language processing, and even those guys, the experts in NLP also know this, right? So, I mean, this needs a lot of work. I mean, and you cannot really, to answer your question, you cannot really actually ask to, you know, ask somebody to stop using one particular word, unless that's a racial slur. So there has to be a dictionary of words which have to be banned completely, that you cannot use in written form in a public domain. I mean, the data which you use, okay? But other than that, it's sort of difficult.
Okay, can I come in that?
Oh, I am just curious why you specifically don't recommend Goodfellow's book. Okay, I think there is another question.
Sorry, who was this? Mr. Manas, is it?
Yes, I can come in. So, in citing that sentence that I am the least beautiful, the problem is that each and every word of it qualifies as a workable word, in the sense that it can be used. I'm sorry for the noise behind, but the whole sentence itself is coming out not in a very appropriate. And there were other instances of sentences in the language app where it was saying that I am the least strong person. So all the words being used are okay to be used in this general scenario, but the meaning, the whole meaning of
right. I mean, the thing is, I think it has got to do with some of the SMS language and the colloquial stuff that has seeped into public domain, right? I mean, when you say I'm the least strong person, that sentence does not make any sense to me even from a grammatical point of view. Okay, so I think my suggestion would be you use one model of English, but the problem with natural language data from public domain is that there are all sorts of English that comes in, right? I mean, there are Indians, there are Chinese, there are Koreans, there are Americans, and then there are British, right? So if you follow while processing, if you follow one standard dictionary, like a Webster or like Oxford sort of an English, then you would actually get rid of some of these sentences while training, or you can rephrase those. I mean, you cannot possibly delete the sentence, but you can possibly rephrase. So before feeding this particular training data into your algorithm, if you see there is a flag raised by some of this, then you can actually rephrase it. Okay. I am curious why you specifically don't recommend Goodfellow's deep learning book. Exactly for the same reason, I don't like the way deep learning research has been conducted. Okay. So if you really want, there are other technical issues. I don't want to overtly criticize the book because this was the first deep learning book that came out, but now you have another deep learning book by Charu Agarwala. Okay. And that makes much more sense to me. I would like to see a deep learning book written exactly in the same manner as a classical machine learning book, like some book by Tip Shirani or Bishop, where you actually build the foundations. Goodfellow doesn't do that. Okay, all right. So he assumes that, he assumes that people who are reading this book are already experts of machine learning, and that may not be the case. In fact, a lot of people actually directly jump to deep learning without taking the classical machine learning courses. Okay. Your point, there are several recent works in de-biasing word embeddings from NLP community. Yes, as I know. That's important, and that has only been last couple of years. For classification, sentiment will be positive or negative for sentiment analysis. If we use SVR, what will be the class level be? Yes, see, sentiments are not really binary. If you really want to simplify it down to positive or negative, then support vector regression is one way to go, but it's a much more complex problem than that. Like, for example, once again, I go back to that tweet retweet example of the airlines, right? The airlines NLP trained model failed to recognize the sarcasm, right? Because it was not trained to them. So sarcasm is a very, very different ballgame, and we use sarcasm all the time. And it's an extremely difficult problem. I'm not blaming it, but there has to be really, I think, another 20-25 years of natural language processing only, where we actually figure out what should be the ideal corpus for training, okay, before we even start talking about the efficiency of those models. Okay.
So, sir, is it that we cannot use SVR for the sentiment analysis then?
You can if it is binary.
Okay, since it is not binary, we cannot use like the...
No, I don't think so. Like, see, for a multi-level, multivariate regression model, because SVR is a regression model, right? It's a support vector regression, right? Yes, you can use, but then what happens is your data becomes like, if you have too many categories in your sentiment, so then your data sort of becomes a continuous one, right? So generally the structure, see, there is this regression problem which can be converted to a classification problem, right? Okay.
Yes.
And lesser the number of categories, the better it is always. If the number of categories become sort of a lot, then it tends to impact the performance. But generally speaking, if it's a binary classification problem, yes, you can use SVR.
So we can just apply the polarity and just categorize the sentiments as positive, very positive, negative, or very negative, like that?
Yes, but also remember, support vector machine on multiple classes is a cottage industry. Okay. So, that there could be another talk on the multi-class support vector machine. Support vector machines are really good for 2-class problems. The moment it is multi-class, it has become a cottage industry, and there is no, in fact, there is a problem in the Voronoi, in fact, the VC dimension and VC scattering point of view. There is serious statistical error in inferencing how good your multi-class support vector machine is. So let's not get into that, but generally speaking, as I said, if it's a binary classification problem, it should work fine. Okay.
Okay, sir. Thank you, sir.
Okay, I think we can conclude the session now. Thank you all for a very wonderful discussion. If anyone has any more questions, you could email Professor Snehanshu, or you could write to NIAS Consciousness Studies Program and we could forward the questions to him. So yeah, thank you all for the discussion. Thank you so much, Snehanshu sir, for the wonderful lecture and for the discussion. I would now invite Hari to give his vote of thanks, a formal vote of thanks for Dr. Snehanshu.
Thank you, Aditi. Thank you, Nitin, for the invitation.
Thank you, Aditi, for giving me this opportunity to give a vote of thanks. I'm Hari Krishnan, Research Associate in NIAS, and also doing PhD under the guidance of Dr. Nitin Nagaraj. So at the outset itself, let me express my gratitude and thankfulness to Head of Consciousness Studies Program, Professor Sangeeta Menon, and to Dr. Nitin Nagaraj, who is an Associate Professor at NIAS, who is instrumental for organizing this workshop. Secondly, I would like to thank the speaker, Professor Snehanshu Saha, for a wonderful and insightful lecture. So basically, what I understood is that there is a lot of very important message for AI enthusiasts. So we should not be only happy with the architectures. We should also question why we should use some architectures, and also the importance of validating the data sets, and asking more and more fundamental questions about the AI bias and so on. Further, so thank you, sir, for this amazing lecture. Further, I would like to thank the coordinators, Niharika Sharma, Aditi, Ashwini, Abhishek, for the wonderful coordination. Last but not the least, I would like to thank all the participants for their time and tuning in for the session. Thank you very much.
Thank you so much. Bye-bye.